Good afternoon, ladies and gentlemen. My name is David Monio. I'm from the Verified Laboratory in Grenoble, attached to CNRS and the University of Grenoble. I'm going to talk about our library for computing of convex polyhedra, the VPL. So why convex polyhedra? Our intended goal with these polyhedra is to use them to express invariants about dynamic systems or programs. So dynamic systems first. If you have a system whose evolution always goes inwards a polyhedron and the initial state of that system lies inside the polyhedron, then at whatever point in time this system, the state of that system, will lie inside the polyhedron. The same applies to programs. You have a control flow graph of a program here. You attach to every control location of that program a convex polyhedron, and then you show that whatever the transitions of the program, if you start in the polyhedron attached to the source location of the transition and you take this step, then you end up in the polyhedron attached to the destination control state of that transition. And then by induction and the number of steps of the program, you can show that your program, the state of your program, always lies in this polyhedra. So you can prove properties. For instance, you can prove that a failure statement is never reached if the polyhedron attached to that statement is empty. Here I have an example where some parts of the invariant are not so obvious. So I have a simple program in which I, at every step, increment one variable and decrement another variable. So the sum of these two variables is always equal to the initial value, because if you add one to one and decrease the other by one, then the sum is always the same. But this invariant, that this sum is always equal to n, is not written anywhere in the program. It's not to be deduced immediately from the syntax. You have to work a bit to see that this is invariant. So we not only want to discover things that are already expressed in the syntax of the program, but also new properties that arise from the dynamic behavior of the system. So what are the difficulties with working of a convex polyhedra? The main difficulty is the so-called curse of dimensionality, which is that the cost of the computations tend to increase exponentially with the number of variables of the program to study, so the dimension of the polyhedra. So what is a traditional approach for computing of convex polyhedra? Most libraries for computing of a convex polyhedra, that is, for instance, the Parametric Polyhedra Library, the Apron Library, Fukuda's libraries also, they use the double description approach. Double description means that for each polyhedron, you keep both a description using generators. These generators are vertices, and for unbounded polyhedra, rays and lines. So you express this polyhedron as a convex O of these generators. And you keep at the same time the constraints. That is, you express that the polyhedron is a solution set of a system of inequalities and equalities. Some of these libraries do not always recompute both description at every step, but in some cases you actually need to do that. And this is important. There is also another important point, that is duality. Whatever happens in one description also happens in the other description, because you can convert one polyhedron to its dual. I mean, the constraints are dual to the generator, the faces are dual to vertices. The operation of convex O is dual to intersection. The inclusion test is dual to the reverse inclusion. So that's important, because any worst case behavior on one description translates by duality to another worst case behavior on the other description. Another important point, these descriptions are not always unique, because you can have redundant elements of these descriptions. So for instance, I have this system of inequalities that describe the blue triangle But one of these inequalities is redundant, the one that expresses the red line. I can remove it without changing the set that is described by the system. And at many points, redundant descriptions create trouble in these libraries. So you need to remove the redundant constraints or the redundant generators, because remember, whatever happens in one description can happen in another description, so you can have also redundant generators. Redundant generator means that you have a point that is already in the convex hull of the other generator, so you can safely remove it. So how do you remove redundant constraints? Constraint is redundant if and only if it is a semantic consequence of the other constraints. And one way to test for that is to show that it's a positive combination of the other constraints. So obviously, if you are a positive combination of the other constraints, you are a consequence of the other constraints. But this is also a necessary condition. I mean, if you are a semantic consequence of the other constraints, then there exists these coefficients. So for instance here, the last constraint, x plus 2y less than 2, is a consequence of the three others. That was a constraint in my blue triangle, the extra constraint. If I multiply the first constraint by 1, and I multiply the third constraint by 2, and I sum them, then I get the redundant constraint. In general, you don't have unicity of representation because of redundancy. But if your polyhedron has a non-empty interior, that is, it's not flat, there is a unique set of irredundant constraints, up to scaling and rearranging. I mean, the ordering of the constraint can change, and you can scale each constraint. So for instance, 2x minus 2 less than 0 is the same thing as x less than 1. And in this case, each constraint defines a true face of the polyhedron. So by elimination of redundant constraints, we get a unique canonical representation, which is very interesting. If you have an empty interior that is a flat polyhedron, this does not hold. And I have an example on this slide. Essentially, this is because the system of equations that describes the subspace in which your polyhedron lives can be used to do substitutions inside your inequalities. And then, because of these substitutions, you don't get a unique irredundant representation. There exists an infinity of irredundant representations. So, how can we recover canonical representations in this case? First of all, you extract the space in which your polyhedron lives. This is called the affine span. So this is done by linear algebra, really. You compute a system of inequalities that describe this affine span. And you orient the equations that define this affine span using a variable ordering. So you decide, and this is arbitrary, that x comes before y, that comes before z. And then you can use these equations as a rewriting system, and you can apply this rewriting system in your inequalities. And in this case, you again have irredundant representation. So once you decide on an ordering of the variables, then you still get the unicity of representation, which is a very important property. So this was the generalities on polyhedra. So what do people do when they do dual description? They generally, there are several ways actually of doing that, of moving from one description to the other. But most libraries use a so-called Chernikov's algorithm, which takes as input one polyhedron defined by generators and one inequality, and outputs the system of generators of the intersection of that polyhedron and this inequality. So if you have a system of inequalities that describes one polyhedron and you wish to convert it to generator, you add each inequality in turn using that procedure. You start with the polyhedron describing a full space, and then you process each inequality in turn until you get a system of generators that describe the polyhedron. This is for going from constraints to generators. But if you're going from generators to constraints, by duality, you just do the same. So for instance, here, I have a polyhedron that is this pyramid. I adding an extra constraint, which is the blue plane. The blue the plane defines an half space that is below the plane. And I'm cutting each edge that has one point on one side of this plane going to a point on the other side of this plane, and then I'm getting extra vertices, the red vertices. So this is basically what Chernikova's algorithm does. Now, this looks very simple, but the double description is not only elegant in this respect, it's also it has also many nice properties. For instance, elimination of redundancy can be done without having to compute the Farkas coefficients, for instance. There are tricks for doing many things. It's very nice description, except for one thing. A very common case in program analysis, and I think also in the analysis of dynamic systems, is when the invariant is a distorted hypercube. That is, you have one interval per variable in the program. It's very common. And such a polyhedron has two n constraints, where n is the number of variables, but 2 to the power of n vertices. Which means that all these libraries, when they go compute the generator description, explode combinatorially. And this is completely unavoidable, because that's not a question of the algorithm, that's a choice of the description. So because of this example with the distorted hypercube, people proposed detecting that a polyhedron can be expressed exactly as a Cartesian product. So the hypercube is a Cartesian product of intervals. But more generally, if your polyhedron can be decomposed into a Cartesian product of several polyhedra, then you should do your double description individually on this polyhedra. So this was suggested by Nicolas Alvax and his students in 2006, and much improved implementation was done in the SNR library in 2017 of this idea. But this won't work if your polyhedron is almost a Cartesian product. That is, for instance, if you have a Cartesian product and then you cut some corners in some places, then it will not be, you will not be able to factor it, and then you will blow up. So instead of doing that, in VPL, we chose a solution only using constraints. So what did we do? We did a constraint-only representation. So what is easy or not in this representation? What is moderately easy is to do the emptiness check or redundancy elimination, because that directly maps to linear programming. So we assume that, there are very good libraries for doing linear programming, so we assume that we can do it. But how do we do projection, and how do we do convex hull? Projection, traditional approach is to do projection using Fourier-Motzkin elimination. So Fourier-Motzkin elimination, you have a system of inequalities describing one polyhedron. You divide these inequalities, you wish to project the variable x, and you divide these inequalities into those that do not mention x, those that mention x with a positive sign, and those that mention x with a negative sign. And then you keep the ones that do not mention x, and you combine each inequality mentioning x positively with each inequality mentioning x negatively, so you get another inequality that does not mention x from that by taking the sum of these two inequalities. And you can show that the resulting system of inequalities is equivalent to there exists x, the original system. So you have actually computed a system of inequalities expressing the projection of the convex polyhedron along variable x. What is the difficulty of that? Well, the algorithm and the proof of correctness of that algorithm are simple, but this algorithm generates a huge volume of redundant constraints. The worst case output of one step of Fourier-Motzkin projection happens when half of your constraints have x positively, half of your constraints have x negatively, and then you get, if n is your number of constraints, you get n squared over 4 constraints after that. So it seems that you could be squaring the number of constraints at every step. And it does not make sense geometrically, because you can show using upper bound theorems on the number of faces of polyhedra that you cannot have this squaring behavior at every step. So this means most of these constraints are actually redundant. So if you're doing Fourier-Motzkin, you're always doing a lot of redundancy elimination, and this is what will cost you. Okay, you can do some heuristics, like for instance, you can, if you have multiple dimensions to project at the same time, you can start with the dimensions that look like they will generate the fewest constraints, and this seems to work quite well to some extent, but still this redundancy elimination is a problem. As I said, linear redundancy elimination can be done by linear programming. There's multiple ways of doing that. You can do it in the primal. I mean, a constraint is redundant with respect to a system of other constraints if it's irredundant. This constraint is irredundant if and only if there is a point that satisfies the system of other constraints but does not satisfy that new constraint. So this means that this new constraint is useful for removing at least one point. So you ask a linear program without an optimization function to provide you with this witness point that your new constraint is actually useful. You can express the same thing as an optimization problem, but really it's the same thing. Or you can go to the dual, and this goes back to Farkat's lemma, to this redundancy witness that I was talking about. A constraint is redundant if and only if it is the positive combinations of the other constraints. So you ask a linear programming problem in a dual. And if you do that many times, it becomes quite costly, because linear programming, okay, it can be done in polynomial time, but it's still expensive. So what are our contributions in this respect? First, we have a fast redundancy elimination algorithm by so-called ray tracing. So the idea here is that we do not improve on the worst case behavior, because in general, in the worst case, this will degenerate to performing the linear programming calls that I was talking about. But in many cases, it solves these redundancy problems right away. So for instance, if I have a point inside my polyhedron, I shoot a ray in one direction, and I meet a constraint along this ray, and this can be solved very quickly. This is just plain linear algebra, very easy linear algebra. Then this first constraint that I meet is irredundant. Another thing is that we replace Fourier-Motzkin elimination by parametric linear programming for doing projection and convex hull. So this is a bit more difficult to explain, but essentially you can show that computing a projection is equivalent to performing parametric linear programming in the dual of the problem, in a kind of dual of the problem. What is parametric linear programming? Normal linear programming means that you take one direction in space, you take your polyhedron, and you give, if the polyhedron is bounded, a vertex that is optimal with respect to this direction. Parametric linear programming means that you, in this case, that you have parameters in the direction of the optimization. And what you do is you output a kind of map of the parameters that say if your parameters satisfy certain inequalities, then your optimal vertex is this vertex. So for instance, if you take as many parameters as the dimension of the space, so you take all possible optimization directions, then you're essentially computing a map of all the vertices of your polyhedron and a kind of cone of directions in which each of these each vertex is the optimal vertex. By duality, and I recall that for doing projection, we're doing that in the dual, what we essentially will be doing will be computing a kind of map of the projected polyhedron. We will have one point inside the projected polyhedron, and we will say, if you look in this cone of directions, then the face that you are looking at is this face. If you go to this other cone, then you will get that face. And if you go to that third cone, you will get that face. So we're computing a map of the faces of the polyhedron. And then we get this constraint description. We can do the same for convex hull. We will obtain a map of the faces of the convex hull. We can actually do projection and convex hull at the same time if we want. So we had to do fast parametric linear programming. And the idea is that some of these computations that could be expensive if done in exact arithmetic, you can actually do them in floating point and still get an exact result. When you're doing linear programming, for instance, you could say, if I call a linear programming solver that is implemented in floating point, then you cannot trust the result if you are into checkable exact computations. But what is important is that your linear programming solver tells you your optimum is this vertex, and it tells you this is this vertex because it's the intersection of this constraint, and this constraint. And this is a discrete information. This is not floating point. You actually get a list of constraints. So if you want to get the exact coordinates of that vertex, you can just do normal linear algebra in arbitrary precision or exact rational numbers and recompute the coordinates of that vertex. And you can check that it is optimal also. You can check that it's truly a solution. You can check that it is optimal, again, by some form of linear algebra. Of course, then you can realize that your library told you incorrect results, but then, if necessary, you can go to exact computation in rational numbers if you want. So to summarize, what we do is we search, perform the expensive search in floating point, and then we perform a check in rational numbers. We can also do parallel computation. What we do for parametric linear programming is a kind of exploration of a region graph. We can explore these regions in parallel. So this is not so easy because you need to check that you're not exploring the same region twice with different processors at the same time. So there's lots of tricks and somewhat intricate details to deal with. But we have implemented that. We have a C++ library for doing that. So what are other applications apart from computing invariance? We have ways to approximate the behavior of nonlinear systems using this parametric linear programming by essentially expressing that higher degree monomials are extra dimensions and doing some forms of projection. So we can actually analyze nonlinear systems or nonlinear programs using only linear arithmetic because of that. So, to conclude, gratuitous advertisement. Our library can be downloaded from this site on GitHub. And of course, I should point out that this is the work of many people. So, Alexis Fouillet, Alexandre Maréchal, and you were PhD students. And there are two other professors involved, Sylvain Boulmé and Michael Perrin. And I'm ready for questions.